Good afternoon, all. Welcome back to the after lunch session. So now our speaker is Irfan Habib from IISc Bangalore. He is going to talk about the symmetric closed subsets of real affine root systems and regular subalgebras.
Hello. Thank you very much. So good afternoon, everyone. Today I'll be talking about symmetric closed subsets of real affine root systems and regular subalgebras. So this is a joint work with Dipnit Viswanath and Venkatesh R. Let us start by defining the notations. Let G naught be a finite dimensional semi-simple Lie algebra and G be an affine Lie algebra. Let H naught be a Cartan subalgebra of G naught and respectively H be a Cartan subalgebra of G. Let phi naught be the set of all roots of G naught, whereas this phi denotes the set of all real roots of G. We denote by delta the set of all roots of G. Let W naught be the Weil group of phi naught and respectively W be the Weil group of phi. So irreducible finite root systems, they are classified in terms of the Dynkin diagrams, or these are the types which are non-isomorphic. Okay, so a subset psi naught of phi naught, this is called a symmetric subset. If alpha belongs to psi naught, will imply minus alpha is inside psi naught. This is called a subroot system if it is invariant under all the reflection it contains. This is called a closed subset if you take two elements alpha beta inside psi naught and the sum is a root, that implies alpha plus beta is inside psi naught. This is called a closed subroot system if psi naught is a closed subset as well as it's a subroot system. For future reference, let us define a subalgebra of G naught to be a regular subalgebra if it is a direct sum of root spaces. Here is an example of finite root system of type G2. Here the collection of all short roots and long roots, they both form subroot systems, but only the set of all long roots, they form a closed subroot system, and set of all short roots, this is a non-closed subroot system. Okay, so this first result is in general true for any coxeter group and its root system, which states that if you take any coxeter group, then the set of all subgroups of the coxeter group, which are generated by reflections, this set is in 1:1 correspondence with set of all subroot systems of the corresponding root system. So in particular, if you take the Weil group of the finite dimensional semi-simple Lie algebra, so that correspondence hold here as well. Even for affine Lie algebra, if you consider the real roots only, then the set of all subroot systems, they are in 1:1 correspondence with all the subgroups of the affine Weil group generated by reflections. This is very exclusive for finite case. Any symmetric closed subsets of phi naught, this is a closed subroot system. This can be proved using root string property. We shall try to understand this, what happens to this statement in the affine case. Also, this is well known that there is a 1:1 correspondence between closed subsets of phi naught and the regular subalgebras of G naught generated by, and the correspondence is given by this. So take any psi naught and you generate the subalgebra together with the Cartan. This correspondence is a 1:1 correspondence. We will address these two questions for affine Lie algebras and we'll see what happens. Okay, so the correct analog for the affine setting is, which is called the real subroot system and real closed subset. You start with a subset psi, and by definition it contains only real roots. It is called a real subroot system or only a subroot system if it is invariant under all the reflections for all the roots it contains, and it is called a closed subset or real closed subset if you take two elements and the sum is a real root, that implies alpha plus beta inside psi. It may happen that alpha plus beta is imaginary, but alpha plus beta is not in psi. Okay. For a symmetric subset of real affine root system phi, we define G of psi to be the subalgebra of the affine Lie algebra generated by G of psi. Again, a subalgebra is called regular if it is a direct sum of root spaces. Okay, so as per the classification of closed subroot system for finite case is concerned, Borel the Siebenthal classified the maximal closed subroot systems in 1949. In 1972, Carter proved that the classification of closed subroot system that can be reduced to the classification of maximal closed subroot system by showing that if you start with a closed subroot system, then there exists a finite chain so that each of the successive inclusion is maximal in that chain. Okay, sorry. Okay, so Dyer and Leher, they classified reflection subgroup of finite affine well group in 2011, but their classification is little less explicit, and it has been made more explicit recently by 2019 by Roy and Venkatesh. And not only they classified maximal closed subgroup system, but also they studied their correspondence with the regular subalgebras of a finely algebra generated by them. Okay, so if you start with a subgroup system Xi, then we can define two things. One is called the gradient, which is the collection of all alpha inside phi naught, so that alpha plus r delta is inside Xi for some r, and for each alpha belongs to the gradient, we can define the z alpha of Xi for all r belongs to z, for which alpha plus r delta is inside Xi. Okay, so if we have these two informations, then we know the information about Xi. The next proposition has been proved by Dyer and Leher in 2011 for untwisted affine root system, and that has been generalized by Roy and Venkatesh in 2019 for any arbitrary affine root system, which states that let Xi be an affine root system, Xi be a subroot system of an affine root system, then there exists a function and non-negative integers in alpha, so that these z alphas are cosets of the subgroup n of alpha. Moreover, this map is z-linear if gradient is reduced, that is, there is no irreducible component which is of type BCN. And we also have this n alpha is in n alpha is same on some w on each w0 orbit. Using that, in 2019, Roy and Venkatesh classified the maximal closed subroot systems. At first, they showed that it is enough to classify irreducible ones, and they showed that there are exactly two types of irreducible maximal closed subroot systems. So the statement says that there exists a z-linear function, a non-negative integer n, so that the Xi is of this form. When m does not divide, m divides n, and if m does not divide n, then Xi is of this form. For short roots and long roots, the subgroups, they are different. And yeah, well, so these two things, these two forms will show up again in our classification. So yeah, just to say that. Okay. And also in the same paper, they studied this map, and they showed that this map is an injection. So if you start with a closed subroot system, and if you map it to the subalgebra generated by Xi, this map defines an injection from the real closed subroot systems and the regular subalgebras. So we'll address this question in what happens. I mean, the question is, can we extend this map? And we'll show that we can't, in fact. Okay. Okay. So our classification starts with, okay, so classification has been done for both reduced and non-reduced, but to avoid technical terms, I'll not present the non-reduced case, but it's there. So it's almost similar. So you start with a symmetric closed subset and decompose it into its irreducible component. It can be shown that each of Xi I, they are symmetric closed. So here is the first classification theorem. We showed that if you start with an irreducible symmetric closed subset, then there are three different forms. Note that the first two forms, they appeared in Roy and Venkatesh list. So they, in particular, they are closed subgroup systems. But this third set of maximal closed, symmetric closed subset, this is new, and we'll show that there are examples in the affine case where symmetric closed subset might not be a closed subgroup system using this example. So yeah, so here is our first theorem using the classification. If you take any symmetric closed subset of an untwisted affine root system, then Xi has to be a closed subroot system. If you remember, so this was exactly the statement for finite case, and we are trying to understand this for affine case. Yeah. Here is one remark: is if Xi is defined by type 3 in the list, I mean the type of subroot system which did not appear in Roy and Venkatesh. So this is a closed subroot system if and only if there are two parameters. I mean, there are two odd integers, A1 and A2. This will define closed subroot system if and only if A1 equal to A2 equal to n by 2. Then only it will be a closed subroot system. So in particular, we have examples where a closed subroot system, symmetric closed subset might not be a closed subroot system. Okay, so we'll now try to understand that map, what was defined in Roy and Venkatesh paper, and we'll try to answer the question whether we can extend this map. Let's see sim G be the set of all symmetric closed subsets, and R of G be the regular subalgebras which are generated by the symmetric closed subset. we define a map as usual. So the first question is, okay, so this map, if you restrict it to the closed subgroup system, this is injective. And we have found out there are examples where maximal, symmetric closed subset might not be a closed subgroup system. So now the question remains whether that extended map is injective. If not, then what is the pre-image for G of psi? We'll answer this question. So first thing is, unlike the finite case, the map is not injective even for, for any G. So here is an example. If you take any affine algebra, which is not of type A2N2, and alpha be a short root, then you can define two symmetric closed subsets which generate the same regular subalgebra. So in particular, the map is not injective for any G. So here is the result, which says that if you take any subclass of set of symmetric closed subsets which contains the closed subgroup system and the restriction of Ig is injective, then the set has to be the set of all closed subgroup system. That means if you want to extend the map from a symmetric closed subset to the closed subgroup system, you can't even extend that map to a single element outside the set of closed subgroup system which retain the injectivity. Okay, and this can be proved in other ways, but it can be thought as a corollary of this proposition. If psi be a symmetric closed subset, then set of all real roots inside the subalgebra G of psi is psi if and only if this psi is a symmetric closed subset. This is a closed subgroup system. Okay. So now here comes the question. Since we have proved that the map is not injective, now we can try to answer the question, what will be the pre-image? And this lemma answers this question. So given any positive integer R, there are exactly phi of two or symmetric real closed subsets in the inverse image such that the integer corresponding to the long root is equal to twice R of n. So if we fix some R, then you will get exactly this phi of two or symmetric closed subsets. And also we also answered the question. So if you take a symmetric closed subset and if you take the inverse image, then what will happen if that inverse image is not singleton? Then we have answered the question, what will be the form of the inverse image? So it says that if you take any inverse image which satisfies this, the integer for the long root is twice Rn, that has to be of the form 2 or 3 in the classification list. We also made it explicit what to choose as A1. This has to be a cyclic generator of the group, the subgroup generated by n inside this group, Z mod twice R n Z. So in particular, the inverse image is infinite. So here is here's the proposition which states for the inverse image. So you take any irreducible real closed subgroup system, then the inverse image is empty. Inverse image is singleton if gradient is not of type A1 or B2, and if gradient is of type B2, then psi has to be given in the classification list. Only in these cases, the inverse image is singleton, and this is infinite for all the other cases. So sorry. Yeah, I'm almost done. I have 3 more slides, I think. Okay, so here are some immediate questions we can try to answer. Does this statement, this set of all real roots of the regular subalgebra generated by psi is equal to psi or not? In general, whether this holds for general Cas-model Lie algebra or extended affine Lie algebra. For rank 2 Cas-model Lie algebra, it is known to be known, and the work has been done by Lisa Carbon and her collaborators. Unfortunately, in an ongoing work, we could prove that this holds in general for Cas-model Lie algebra. So yeah, what happens for the extended affine Lie algebras? That is a question. So yeah, that might be interesting to try to see. Again, okay, there is one other question. What are all the imaginary roots inside the subalgebra generated by psi? We don't know the answer even for rank 2 Cas-model algebra. We don't have any description of imaginary roots which can appear there. Okay, the third thing, do you have any geometric description of maximal closed subroot systems of a fine root system? Because in the Borel-Subenthal's classification, the classification was dependent on geometric ideas. They use simplices and those Cox-Zeta complex, those things to classify the thing, but we don't know whether there is any analogous analogous idea, analogous description for a affine root system that we don't know. Here are all the references used. So this is our paper, and this is the paper of Roy and Venkatesh. This is a paper of Douglas and Graf. They are the classified closed subsets of finite root system by decomposing it into symmetric and special part. They classified symmetric part, and for special part they gave an algorithm. They gave an algorithm to prove for the special part. Here is the paper for Boril the Simenthal, and these are two papers where in one paper the reflections subgroups of finite or affine well groups has been classified, and here the paper in which they classified in some sense untwisted affine root systems, the subroot system of untwisted affine root systems. Okay, thank you for your attention. Any questions?
Are there any questions? Okay, not let me thank the speaker again.
Thank you very much. Start.
Next speaker is Dibyendu Viswas from IIT Bombay. He is going to talk about branching laws for symplectic groups.
Hello. Thank you, the organizer, for giving this opportunity to talk here. So today I will talk on branching laws for symplectic groups. Before going to start, so I just want to tell why this project or problem came in my mind. So actually I was doing branching problem from GLN to GLN minus 2 and SP2N to SP2N minus 2 and find some good relation. And from doing this, and then I tried some general thing, and then some results came. So it's for all groups, for GLN symplectic or orthogonal, even orthogonal. But today I will present for the only symplectic groups. Okay, so just before branching, so this is the restriction. Sometimes it's called branching rules. So we know restriction induction from our early age. This is restriction. So you take two groups, H and G. G is the bigger group, H is the smaller group, and we want to restrict one representation from bigger group to smaller group. Okay, so we will consider finite dimensional irreducible representations, and we think V as a H modules for the smaller subgroup. And why I took reductive? So I have to make sure that this completely reducible. Otherwise, I can't talk about branching problem. So if you take reductive groups, then it will completely reducible, and some constituent will come. So these WIs are the irreducible representation for H. So these WIs can repeat. It can happen that W1 and W2 are the same. So if there is no repetitions, then we call this branching is multiplicity free. Okay, so now today symplectic group. So symplectic group sp2nc. This is the 2n by 2n matrices. This is defined is this way, where J is the skew-symmetric matrix. Okay, sp2n obviously is a subgroup of GL2nc, and my talk is, so our all groups are over complex numbers. So I will denote sp2n instead of sp2nc, and this has a, so like sp2n minus 2 sits inside sp2n. It's a very good way. Here we start J, take I equal to n by n. So if you take I equal to n minus 1 times s minus 1, then you will get corresponding sp2n minus 2. Okay, so before, so this is the some already in 2 talks, morning session, we know the what are the highest weights. So irreducible representation for symplectic group is also parameterized by highest weights, and it's so we are talking about sp2n. So it will come as an n tuple of integers, and having this condition lambda 1 greater or equal to lambda 2 up to lambda n, and so we denote pi lambda corresponding to the irreducible representation for lambda. Okay, so now let's talk about the problem. What is the problem before going to further? So this is the, I take a irreducible representation pi lambda, and I want to restrict from the G is the sp2n and H is sp2m, and I want to know which mu appears. So this is the 2 things we want to understand. So which mu appears, what is the meaning? Mu appears means that is C lambda comma mu, or if some mu is appears, that should be non-zero. That means that mu is appearing. And if it is non-zero, then the next question is, what is the multiplicity? Like, what is the cardinality of this C lambda mu? So for this problem, this is the current status. So from 1973 Golobenko's paper, if you take m equal to n minus 1, so this is known. But for the other arbitrary m, it is known in the not known in the sense that there is no explicit description of C lambda mu in a very good way. So this is the overview of whole things. So this is the known scenario. These are the 4 known cases we know mostly, and these are the new one can. So this is GLN to GLN minus 1 known. Everyone knows that that comes as an interlacing property. So, but in the literature there is not known even GLN to GLM minus 1. There is something Gelfand-Gatlin basis, and those things are there, but no direct formula for C lambda mu. So today I will talk only symplectic part. So those are colored by red. So this is the known part. The problem is I take m equal to n minus 1. So that is sp2n to sp2n minus 2. And the question is again 2 questions I ask: which mu appears and what is the multiplicity? So this is the question, which mu appears. So here mu is a n minus 1 tuple. So it's enough to, if I know that, what are the mu i's, and these mu i's are guided by this equation. So you see j equal to 1 to n minus 1. So these mu i's are guided by these inequalities. So from there you will know which mu I appears. And then it says that this C lambda mu, that's cardinality, is a product of k many product of n many integers, and that all kj is coming as a, if see xj minus yj plus 1, and this xj yj coming as a some beautiful way. So x1 y1 up to xn yn, there are 2n many integers, as I write non-increasing way. So that's actually rearrangement of lambda 1 up to lambda n, mu 1 up to mu n minus 1 and 0. So if you write non-increasing manner, then whatever you get, and from there you will get kg. And if you just take this product formula, you will know the branching laws for sp2n to sp2n minus 2. This is the known part. So the scenario is that this C lambda mu coming as a product formula, it's we are lucky, we are in the very ground case. Some sp2 is behind, sp2 is lurking behind, so that's why this product formula is coming. But for the general one, we rarely hope that this kind of things will come. Okay, just a remark. So you see this product formula. So this is a special. So this comes after some stage. So before, so this is come from a matrix, and that matrix looks like this matrix MIG. So that formula, if the brute force, if you calculate determinant of this matrix, one get this good beautiful product formula, and due to sp2 is there. So that's why that was easy. So what is this? So lambda is and mu is are those weights. So you calculate lambda. So this is m ij means ijth coordinate of m. So it says that lambda I minus mu j plus j minus I plus 1 and then plus. This is a notation. So the notation is something a plus. It means that if a is a positive integer, then it's a, otherwise is 0. Like if you take minus 2 plus, then it is 0. If you take 3 plus, then it's 3. 0 plus is also 0. So you see, so I was doing this, so I don't have, so you just remember, or maybe you can think this a plus actually a choose 1, nothing but a choose 1. Because if a choose 1, if a is greater or equal to 1, that is a. Okay. So when we generalize this, you will see how beautifully this will come there. So from this perspective, we don't understand how this happening, but if you go there and put our and see ground case, then it will come very beautifully. Okay, so just to get an idea, so this is the very ground case sp6 to sp4, sp6 to sp4, gap is 2. So it will be a 3 by 3 matrix, rank of sp6 is 3. So it will be a 3 by 3 matrix, and this coefficient is coming this as a. So lambda 1 minus 1, lambda 1 minus 1, mu 1 plus 1, choose 1, and so on. So you keep remember this also. This will come again in the general one. So these two things we should remember because it will again appear. Just example how actually what we are talking about. So this 2 to 1, this is a irreducible representation. This is the highest weight corresponding to irreducible representation. If you take and you restrict from sp6 to sp4, you will get this decomposition where this 1 0 appears 1 times. Those 1 start 1 0 means 1 0 appears 1 times, and this is the and 2 1 similarly 2 1 appears 4 times. So our target is that from arbitrary here sp6 to sp4 is only gap is 2, but it can one can ask from sp100 to sp50 or sp1000 to sp100. What will be this coefficient? So that is the challenging one. So this is our trying. We will see. So this is the new result. Again, this is the problem. sp2n to sp2m. I choose m anything lesser than lesser equal to m minus 1, anything, and the formula is coming. So you see, previously it was there I plus 2. This lambda I greater or equal to mu I greater or equal to lambda I plus 2, because that time n minus m is 1. So we just got this formula. So I mean, one can guess or one can get easily this formula using induction. This is somewhat easy to get, but this next combinatorial formula, I will say this may not be easy to guess or to get it. So this is the big formula. So it says that this multiplicity comes as a determinant of a matrix, and that matrix whose ijth entry is given by this formula, uij plus kj j. And what is uij? Uij is lambda I minus mu j plus j minus I. We already seen this expression lambda I minus mu j plus j minus I earlier. And what is kj? You see, so here I restrict from sp2n to sp2m. So let's take example sp100 to sp40. That m is 40, n is 100. So it says that the first 40 columns, that is j is 1 to m, it is a constant. So kj is constant. 2n minus 2m minus 1. N is constant. N I took 100. M I took 40. So 2n minus 2m minus 1, that is a fixed number. But the latter 60 columns, there is some changing. And what is the changing? That depends on j. And it is 2n minus 2j plus 1. So this is the way you got kj. So this is actually a big matrix, whose each entry is a binomial coefficient, and those binomial coefficient is given by this. So this is the general statement. So just example, if you take same I took 2 to 1, I keep just consistent. Now sp6 to sp2, gap is 4. Okay, so that means lambda 1 mu 1, this is 1 plus 4 is 5, and in this scenario lambda 5 is 0. That we set in the theorem. Here I forgot to tell, lambda n plus I is 0, mu m plus I is 0. So this is lambda1 greater equal to mu1 greater equal to lambda5. So mu1 is in between 2 and 0. So the option is 0, 1, and 2. So this 3 will certainly appear, but the question is that how? What is its multiplicity? So it says that it will be 20 times, 29 times, and 16 times. So I choose cardinality of 1 to show. So corresponding to this, the matrix, I tell that it will be a big matrix whose every entry will be a combinatorial. So this is I took from SP6, so it will be 3. The rank of SP6 is 3. So it is a 3 by 3 matrix whose ijth entry is given by this. So just let's take 2, 2 entry. So it will be lambda2 minus 2 plus 2 minus 2, and then some 3 and choose 3. So in this scenario, here it is K1 is 3, K2 is 3, and this K3 is 1. That will come as a, I think, the first one is coming maybe 6 minus 4, and then minus 1. No, this is plus 1. I wrote it just. Yeah, so the first 3 is coming as a, yeah, I was right. 6 minus 2 minus 1, this is 3. This is my K1. And then 6 minus 4 plus 1, this is also 3. This is K2. And then 6 minus 6 plus 1, this is 1. This is my K3. So this is coming. And now we specifically want to calculate how this 29 is coming. So if you just put mu1 equal to 1, and if you have to put all the values of lambda is and mu is, certainly mu2 and mu3 is 0. And if you put all the things, so it will come as this, and if you calculate this determinant, that determinant will come as a 29. So just a cross check, one can do this brute force or manually. So one has to go from SP6 to SP4, and then SP4 to SP2, and one can calculate that one will certainly appear as a 29 times. So this will come certainly. Okay, so just to give some outline, it's a big, it will be a long proof. So mostly I did not use any combinatorial result or formula. I use Wildcatter formula, certainly. So you have to use Wildcatter formula, both H and G, 2 groups are there. And then there is a big expression for L'Hopital rule, and then general partition function. And then finally your multiplicity will come as this beautiful formula. So this is the thing you actually get. So that's why it's come as a determinant. So this is the formula is summation over, if you remember the determinant formula, summation over Sn, sin S, and then product of n minis. So these are the first m minis are coming. So here 2r minus 1, 2r minus r is n minus m. So it's matching with our entry. So the first m for the first m column, it is this ki's are the fixed, but here they are varies. So this comes as a multiplicity C lambda mu. So then question is what is the next? Certainly this one can get for the other groups, like from GLN to GLM any. I choose symplectic because it is less trivial, and something is there. For the GLN scenario, you see there is I got 3, 3, 1, 2 gap. In the GLN scenario, it will be 1 gap only. Okay. And odd orthogonal case, some similar minus half will come somewhere. Those are the little bit difficult expressions, but it will come again as a determinant of a combinatorial matrix. So the question is that matrix, I just gave I just tell one can get how many times appears. So one has to calculate the determinant. But further simplified expression, one can ask, what we have m equal to n minus 1 scenario, it's a product of j many integers. So in this scenario, one can ask this question. And then next question, has it any connection with combinatorics and graph theory? Certainly, it's a n by n matrix, and whose entries are coming from, one can think in directed graph. This side you have n many tuples, that side n many tuples, and you have some edges. I don't know, is there any connection or not? And then the third is very, this was interesting. So can one bridge these formulas to wild dimension formula? Here what I did, SP, to n to any SP, but I never go to SP0. If can one go from SP2 to SP0, then actually we will get wild dimension formula. So can one put all together in one frame, then maybe that will be the generalization of wild dimension formula. That can be another good thing. So the references is this Goodman-Wallach, what I state for SP2n to 2n minus 2, that you can see in Goodman-Wallach. The next two references is, this is from 1973, those that which muages appear, and these two references is that the product formula for SP2n to SP2n minus 2, that is there. This is the Miller did that work, and this, thank you.
Are there any questions?
This is just a comment, but whenever you have a determinant of binomial coefficients, there's a natural combinatorial interpretation, which is as a series of as a counting of non-intersecting lattice paths.
Yes, maybe you are talking about
Gessel
LGV lemma.
Yeah, this is called the Gessel-Vienno.
Yeah, Gessel-Vienno lemma. Yeah,
So maybe
I don't know, is there any connection or not, but it may be.
Yeah.
Because there is also some AI, BI comes. There should be some connection, but till I don't have any known knowledge or things.
Another way of interpreting the multiplicity for symplectic would be to count doubly interlacing things. In the case of symplectic, right?
I mean,
For going from
what is
SP2n
the
to
definition
SP2n
of
minus
doubly
2.
interlacing links?
So, like I have got lambda and mu. I'll try to find how many nu are there which are interlacing lambda.
Yes, yes, correct. That can come. That will come. So one can get those, I tell that lambda I greater or equal to mu I greater or equal to lambda I plus 2n minus m. That expression, how one can get, you have a big matrix, you calculate when it is non-zero. From there you can get, otherwise you know the two gap, and just you take the induction, each step 2, 2, 2. Then you will get the.
I'm not talking about the
one.
gap part. That would say that, I mean, that would tell you the part that lambda I is greater than mu I is greater than lambda I minus 2m plus n, whatever the formula you had got.
Yes.
Right? I'm saying that one can count the multiplicity as well using that formula. As in the case of, I know this for just the case of SP2n to SP2n minus 2, that just counting the number of things.
Yes, yes. From SP2n to SP2n minus 2, it is lambda I greater or equal to mu I greater or equal to lambda I plus 2, because these two actually coming as a 2n minus 2. For the general case, it will come as a 2n minus 2m.
What I'm saying is that if I want to look at that multiplicity C lambda mu,
yes,
that is equals to number of nu, such that lambda.
Correct, exactly.
Lambda 1 greater than mu 1 greater than that
but
thing.
But the question is that huge interlacing, how, I don't know. So that's
that would also exactly follow and give a binomial coefficient on.
Yeah, one can, obviously. I mean, those guesses I got only doing this. And then I go and I using Wildcatter formula and this. I mean, if you are going from arbitrary, let's say SP 5000 to SP 500, how do you go from every step? There are so many steps. So you have to use Wildcatter formula. I don't know, is there any other method? So just maybe here, so this is, you see, this first m, this actually coming from partition function, and the latter, this part is actually coming from a using some L orbital rule. So this is the beautiful thing is coming here. That's why this total n term, first m term due to partition function.
Okay, so if you have more doubts, you can discuss with the speaker later. And once again, we can thank the speaker.